So the next balance law that we are going to look at is the balance of energy, and uh, for the derivations that I'm going to do now, we are going to invoke the first law of thermodynamics. So we are going to look at the application of the first law of thermodynamics to that to a deforming solid. Now consider the deformed volume of deformed configuration omega. It has um, tractions applied on the boundary, it has body forces, and consider a small volume d small v, which has a velocity v small x. So the power expended in the small volume is b dot v. The power supplied in the small volume is b dot v integrated over the whole volume. Similarly, the power expended by all the surface tractions is T dot V ds. So this constitutes the external power that is supplied to the body through the tractions and the body forces. So this external power goes into increasing the kinetic energy and the internal energy of the body, internal and does work on the body. This work done, or this power expended, is given by sigma d integrated over the volume. So this is the power expended per unit deformed volume. This is the rate of change of the kinetic energy. The kinetic energy of the small volume is half rho uh, v square, where v square is v dot v times dv integrated over the whole volume, and ddt of that is the rate of change of the kinetic energy. So the rate of change of the kinetic energy plus the stress power that is expended has to equal the external power that is supplied. Now this, as I said, sigma times d is the power expended per unit deformed body. Now, we can look at this term in different other ways. We can try to find out, for example, the power expended per unit undeformed volume. That's what we are going to do now. So, this is my stress power, and this quantity is stress power expended per unit deformed volume. If I want the stress power expended per unit undeformed volume, I have to change the domain of integration, and to do that I will simply have to multiply it by j, so that this becomes d capital V. So the domain of integration changes. So this quantity is now my stress power expended per unit reference volume. I can express this in terms of other stress measures, and to do that, first let us remember this expression that we had derived, E dot equal to F transpose dF. We had derived this earlier, which means that D is equal to F minus transpose E dot F, or in initial notation Dij is F inverse, let's say Ki E dot KL F Lj. So this is your Dij, and I'm evaluating J sigma ij Dij, which is J sigma ij F Ki inverse E KL F Lj. That's now I take the sigma terms together, which make it J F Ki inverse sigma ij F Lj inverse E dot KL dot E dot EKL. Now remember that S is equal to J F inverse sigma F inverse transpose. This is the relation between the second peak stress and sigma. And if you look at this closely, you will see that this is SKL EKL dot. So J sigma dot D is same as S dot E. So the stress power, the total stress power can be written as S dot E dV over uh, integrated over the reference configuration. So this quantity gives you power expended per unit reference volume. Uh, it is also easy to show, and I leave it to you to show that this can be expressed as P. So P dotted with F dot also gives you the stress power expended per unit reference configuration. So these three expressions, sigma dot D integrated over the current configuration, S dot E, SE dot integrated over the reference configuration, PF dot integrated over the reference configuration, all of them give you the total stress power expended by the body. And these are called conjugate measures. These together give you the stress power, and these are called conjugate measures, which means that S is conjugate to E dot, P is conjugate to F dot, sigma is conjugate to D. So with this in place, now let us look at the rest of the balance of energy. Now uh, the balance of energy also involves the transfer of heat, and assume that let us imagine that the deformed configuration, other than deforming and experiencing stresses and strains, is also uh, subjected to transfer of heat. So there is heat leaving or entering the system. So this is the heat, Q is the heat flux, outward heat flux. So the net heat, uh, the heat flux is Q dot N, and that integrated over the boundary of the body gives you the total heat leaving the system. Uh, in general, heat flux, heat entering the system is taken as positive, so this is taken as negative. Heat leaving the system, net heat leaving the system, is taken as negative. And then there is analogous to the body force for every volume. R is the volumetric rate of heat generation. So R is the heat generated within the body, um, due to, say, chemical reactions or nuclear fission or whatever taking place. That gives you the total heat generated. It's R dV integrated over the whole volume. So this gives you the rate of heat transfer. So uh, includes the rate of heat generated within the body and the rate of heat, rate at which heat is leaving or entering the body, or the heat flux, with the condition that if the heat flux is in the direction opposite to the normal, which means Q dot N is negative, then heat flux is taken as a positive quantity. Now this is the rate of heat transfer. This is the rate of heat transfer in the deformed configuration. We can also write it in the undeformed configuration. So just like we had defined the traction and its connection with the undeformed normal, we have to make the assumption that the total heat flux, so this is not the only way, but one of the ways is to say that the total heat flux, so Q, capital Q dot N D capital S, this is the total heat flux, is equal in both the deformed and undeformed configurations. So if this is assumed, and we assume that point to point Q dot n is equal to q. Every point, the capital Q is such that capital Q dotted with the reference normal is equal to small q dotted with the current normal times d capital S and times d small s. Then we can use the Nansen's relation here. Then we can write q n dot d capital S equal to q dot j f minus transpose n d capital S, which means that we now get capital Q as j f inverse q. So this is the heat flux vector in the reference configuration, and q dot such that in such a way, derived in such a way that at every small area element d capital S, the heat flux is same, whether you calculate it in the reference or in the current configuration. So this was the assumption that is made, and this assumption leads to this definition of the uh, heat flux, the heat vector. This is the heat vector in the reference configuration. Now here is your first law of thermodynamics in rate form. Uh, the work done, that is the stress work done, and the heat supplied, the rate of heat supplied is equal to rate of change of the internal energy, where the internal energy is given by this quantity E. Now we are going to define a internal energy per unit mass. So we are going to define a specific quantity EC, which is internal energy per unit mass, which means that for a small volume dV, its mass is rho times dV, and its internal energy is EC, and that integrated over the whole volume will give you the total internal energy, that is, it will give you this E, and then we will take the ddt of E, that is the rate of change of the total internal energy. So that is the rate form of the first law of thermodynamics. So this side is ddt of rho EC dV. Okay, now we have P int here. The P int we have already figured out is sigma dV, sigma d d small v. So that's what we have for P int. And for Q, we have figured out in the previous slide that Q, the rate of heat transfer, is the rate of heat leaving or entering the system, the net heat flux, plus the rate of heat generation in the body. So we just take it as it is, and we have Q dot N dV. So this term is of course Qk Nk ds, which with the application of divergence theorem will become del del xk of Qk dV, and this is expressed in vectorial form as divergence of Q dV. So now you have sigma times d dV, Q divergence of Q dV, and then R dV, and here I have converted into dV by taking this specific quantity, and that becomes ddt of rho EC. So now again apply the localization argument, and then what you get. So this term will have to do a little bit of effort. Um, let's do that in the next slide. So we have ddt of rho EC d small v integrated over v, and if you remember, we had already made the argument that you cannot take this ddt inside because this is a function of time. So what we do is we write ddt of omega naught rho j rho EC d capital V. Now this is no longer a function of time, so I can take this inside, ddt of j rho ec dv d capital V. And this will be equal to uh, j dot rho plus j rho dot times ec plus j rho ec dot d capital V. Now concentrate on this term. So j dot we know is j trace d, which is j del vk del xk. We had proved this before. And rho dot, remember this is the total derivative. Rho dot will be del rho del t plus del rho del xk dxk del xk del t, which is same as vk. So this is equal to j times del vk del xk plus there's a row here, I missed it. So it is rho times del vk del xk plus del rho del xk vk plus del rho del t. And these two terms together is del xk of rho vk plus del rho del t. So this is what I have from the first term, and you will recall that from my balance of mass, this part is equal to 0. So balance of mass gives that this part is equal to 0. So this is equal to 0. So I am left with, from here, left with j rho ec dv, sorry, ec dot dv, and I again club the j and this dv together to change the domain again. So I make it rho ec dot d small v. So that becomes integral rho capital ddt of ec d small v. So once I have done this, now I have handled this term. Now everything is d small v. I can use the localization argument and I get rho ddt of ec on one side and these things on the other. So this is my expression for the first law of thermodynamics for energy balance in the deformed configuration. So this is a very important equation that we are going to use. Now we can write this in the undeformed configuration also. To do that, we first have to write this statement in the undeformed configuration. So to write that in the undeformed configuration, we already know that sigma d is same as, let's say, S E dot d capital V over the undeformed configuration. We have defined a capital Q so that the total flux is capital Q dot N d capital S. So we have defined capital Q, remember, as J F inverse Q. This was defined a few slides ago, and then this we can define some R naught, which is equal to J dV. So we can define R naught d capital V over. So this is what becomes of the left hand side of this equation. When you do apply the divergence theorem to this quantity, this will obviously become the second term on the left will become this. Okay, so here you will be left with S E dot minus divergence of capital Q plus R naught, and then you will have to define here in place of EC we will define something called EC, let's say E naught, so that E naught is the strain energy stored per unit undeformed volume, undeformed mass. So this is strained energy, internal energy stored, sorry, internal energy stored per unit undeformed mass. Undeformed mass. So that ddt of rho naught E naught dV is the rate of change of the internal energy. Now apply localization argument to this, you will get rho naught E naught is equal to this as your first um, energy equation in the reference configuration. If I use instead of this, if I use P F dot, which we have again shown earlier that is equal to sigma dot T, then uh, we get this equation. So both of these are in the reference configuration. In both of these are statements of balance of energy in the reference configuration.